Um, welcome everyone to today's video. Uh, so today we'll be continuing with our chapter of fluid mechanics, and we'll be taking today the topic of barometer. So let's begin. So um, basically, what is a barometer? So barometer is a device which is used to measure atmospheric pressure. So atmospheric pressure is like an important quantity. It is used to measure uh, what is the temperature at a particular point. It is used to measure what is the probability of a storm coming in certain areas. So it is a very good indicator of that, which is still used to this day. Basically, it is a device which contains some kind of, or in the earlier times, it was a device which had some kind of mercury bath. And then there is a tube which is inverted and it is put in the mercury bath. How it looks like? So this is how it looks like. This is the mercury, and this mercury it is put inside this bath. So as this mercury is put inside the bath and we invert a tube like this, the mercury enters this tube. And why is that? Because we have created a vacuum at the top of the tube. So because of that, there is a pressure difference between the topmost point and bottommost point. And the mercury outside in the bath, it rushes inside this tube to fill up the tube. But it fills up only up to a certain point. So how does this happen actually? So to do that, we select different points. Let us take the topmost point as A. The point which is in the level of the mercury bath is B, and this point as C. So this is A, this is B, and this is C. I hope that is clear. So now let's begin. So our objective here is to evaluate how does it measure atmospheric pressure, right? So here we have said there is a vacuum created over here at the top. So it is basically mercury vapors. This is all the mercury vapors, right? And this is mercury, and now basically it is surrounded by atmosphere, and atmosphere is exerting a pressure. So you know that the pressure exerted by the atmosphere at sea is same as that by atmosphere. So this is atmospheric pressure. So atmospheric pressure, as we have learned already, it is represented by P naught. So since sea is open to atmosphere, the pressure at sea is atmospheric pressure. So there is always, so there is a lot of air surrounding this whole setup, and it is exerting a pressure at sea. Our objective is to evaluate what is the height to which mercury will rise inside this U2, that is H. So you might be getting some intuition that if we increase the atmospheric pressure at point C, more and more fluid will rush in this U2 to increase the height H. And your thinking is absolutely correct. This pressure P naught is actually what is forcing the fluid inside this tube. Let's see how. So pressure at point A, let's say whatever pressure that A is. So adding the pressure of this fluid over here and pressure at point A. So we know that this pressure due to height h of fluid of density rho and height h is this. So this is PA plus rho g h. This will be equal to pressure at point P. So this is the equation which we have learned, pressure at a depth h in a fluid. And the same equation we can apply here, which is great for us. Here we have to note rho is density of mercury and its value is some 13.6 into 10 to the power 3 kg per meter cube. Now, so what would be the next step? So I have guessed it right. The next step is we will be equating the pressure at point B and at point C. These two pressures are equal. So why are they equal? Because they are lying in the same horizontal line in a fluid which is at rest. So as per Pascal's law, the pressure at 2 points in a horizontal line is equal. Pressure at point B is equal to pressure at point C. So we can write in this equation here, we have PB, instead of PB we can write PC is equal to PA plus rho GH. Whereas we already know PC is equal to P naught and PA is nearly 0. This vacuum which we have created here uh, by sucking out all the air which was in this tube is called Torricelli vacuum. So we will say the pressure is very close to 0. So this PA is 0. This is rho P H is equal to P naught. So this is the equation which we are looking for. Practically, uh, when we determine what is the value of H, its value comes out to be some 72 centimeter. So this also becomes a unit of pressure. That 72 centimeters of mercury shows this amount of pressure. So let's do a question. The question is, I have a barometer which is placed in an elevator. That elevator is accelerating upwards with an acceleration A. This whole setup is accelerating upwards with some A acceleration. And the height h of mercury in this fluid reduces to 48 centimeters. That is the height of the mercury in this container reduces when I'm accelerating the whole setup with an acceleration A in vertically upward direction. We have to find what is A. So if we know what our equation of uh, pressure is, atmospheric pressure equation is, it is P naught plus rho GH. So even if I'm accelerating and the whole setup upwards is not going to change the atmospheric pressure as much because we are in the elevator. Its pressure does not change because it is simply accelerating. The pressure is going to remain P naught only. G is going to change because in an accelerated fluid we add a term of acceleration A to the value of G so that it becomes the net acceleration. Density will remain the same and H is going to change. So we know rho gh, the earlier value of rho gh what we had was equal to the atmospheric pressure earlier. Now its value has changed to rho g plus a into h dash. So h was the earlier value of height of the mercury, and h dash, this is the new height. So this h dash, the value which we have taken 48, this is the value h dash. So we'll put that value here. So what we'll get? Density of the mercury remains same as is. So this is simply G into earlier height h, which was 72 centimeter, G plus A into h dash. The value of h dash is 48. That is, the new height has reduced. Mercury's height has gone down because the fluid is accelerating in upward direction. So uh, we can say this value of G, this is 72 by 48. 72 by 48, this is simply 3 by 2 into G is equal to G plus A, or this implies A is equal to G by 2. We can put the value of A here to get the value of acceleration as 4.8 meter per second square if G is equal to 9.8. So this was one of the questions. Now we are going to study what is the pressure difference in a fluid accelerated vertically, in a fluid accelerated horizontally, and a fluid rotated about its axis. So let's do all the three cases. So we already studied the case when an container is placed like this and we are accelerating the fluid in upward direction. So when we are accelerating the fluid in upward direction and the density of the fluid is some rho, could you imagine one of the real life cases where this could happen? So if we think about stars and sun, this can be one of the cases. Often in cases of rocket fuels, we use liquefied gases which are accelerating upwards with very high speeds, with very high accelerations. In those cases, the same thing happens. The whole container is accelerating upwards. So what is the pressure difference created? One of the questions can be asked. So one cases can be that. One of other cases could be uh, even a simple case like we are talking about milk. So let's say milk is there and it is of varying density. So we want to separate different densities of the fluid of the milk particles. So how do we do that? How do we accelerate a fluid without moving it horizontally or vertically? So we can rotate it. In case of rotation, we already know that the particles which are of higher density, they get thrown to higher uh, distances from the axis, and the particles which are of lower density, they remain close to the axis. So this is one of the principles which we can use. In those cases, how do we calculate the pressure difference? How is pressure difference important in such cases? So of course, we can obviously do these experiments practically, but having a theoretical idea, okay, what pressure difference uh, which will get after accelerating the fluids at a high acceleration, it gives us a great perspective. So if I'm accelerating a fluid in vertical direction, we know pressure difference in an vertically accelerated fluid. Its value can be calculated by using pseudo forces. So if I have a observer which is attached to this container, it will see that the fluid particles will experience a pseudo force Ma in addition to the gravitational force mg. So this means that the gravitational force mg is supplemented or is held on its way by the pseudo force Ma. So this means that wherever this g factor is coming, which is coming in this equation, will be accompanied by this a factor if the container is accelerating vertically upwards. So g plus a into whatever height difference we are taking, let's say height difference h we are taking. So multiplying with that, the density will give us the pressure difference between the point E and the point B. So this is the pressure difference in vertically accelerated fluids. Next, pressure difference in uh, horizontally accelerated fluid. One of the interesting cases, if I have a fluid container like this, I accelerate a fluid horizontally. So how will the fluid surfaces change? What will be the angle the fluid surface would be making with the horizontal, this angle theta. So this tan theta is very conveniently equal to a by g. We want to see why this tan theta is equal to a by g. The answer lies in the idea that if I take 2 points in this container and I compare their vertical height and their horizontal distances. So as the acceleration is happening in horizontal direction, if I place an observer in the frame of reference of the container, right, so there will be a pseudo force. Right? The pseudo force will be acting on the particles in this fluid. Now, this pseudo force which is acting, it is creating a pressure in the fluid. So we know that when we go from direction A, from point A to point B, the pressure is going to increase because of this pseudo force M. So they act in the same way as mg. If mg was acting in vertical direction, it would create a vertical pressure difference, and which is equal to rho g h. In the same way, if there is a pseudo force acting horizontally, it will create a pressure difference like that. And when we go in direction of these forces, we know the pressure is increasing. That means the pressure at point B is more than pressure at point E by the value rho g or rho a, whatever the strength is. Let's say L, right? So rho a L, that is my pressure difference between points B and A. But what about the vertical height? Can I use the vertical height to calculate the pressure difference? So vertically speaking, uh, A is A and B have a height difference equal to this particular triangle, right? This height h, the small distance h, if it is visible to you. This h distance is the vertical difference between points A and B, which is creating the pressure difference. So you see again, pressure at D is equal to pressure at A plus this extra pressure created by the height difference, that is rho g h. So if we compare these two equations, it can easily say here rho A L is equal to rho g h, and this implies h upon L is equal to A upon g. From this triangle, we can see that if this angle is theta, so as this angle is theta, I can say h upon L is equal to A by g, or A by g is equal to tan theta. Now, one of the interesting cases we'll take. We'll take a case of a fluid which is already put in a rotating setup. So the fluid particles are rotating. The pressure differences in case of a rotating fluid. Rotating fluid. Here by rotation we mean that there is a container and all the particles are already put in circular motion about this axis like this. So they are moving like in a circular motion. This angular speed is given to us as omega, and the surface kind of forms like this. So this we already know from a practical experience. You would have done this at home, right? We will not need to travel in a spacecraft or do experiments with whatever fluid to experience this. Let's say if you were at home and you had a lot of water and you want to basically, let's say the water is too hot, so you are using that container which you have to creating this whirlpool, and when this whirlpool is created you see a surface forming. So this is our attempt in finding this is a parabolic kind of surface. So what is the equation of the surface that we can find? So how do we do that? So let's say if at point B, uh, these are 2 points in a horizontal line, and this is a point C vertically above point B. So we already know pressure at point B is equal to pressure at point C plus rho G. Whatever vertical height this have, we have here CB. So this height is some y, right? So let's say this is y, and this is the origin. Oh, right. Now, so we'll now begin stirring this fluid. We'll put our hand in the container, in the tub, and we'll boil it. Okay. We just have to make sure that the tub does not contain very hot water. है We just want to create a whirlpool like that. So when we are creating a whirlpool, we are giving it an angular speed, angular velocity. So what do you think will happen if I increase the speed with which I am whirling the water particles? The parabola will become even more sharp. That is the particles at the side of the tub will rise high, and the particles at the center of the whirlpool they will go even lower. In fact, if you whirl it very fast, you can even see the bottom of the tub. So uh, this distance is x. So we create an equation of pressure difference at some x distance from this axis. So how do we do that? So let's draw a figure again. Let's say we are considering these fluid particles like this. These are the fluid particles which we are considering. The cylinder you can consider, right? So now at some x distance, we are taking this small section of the fluid dx like this. So this is the dx section of the fluid, right? And what this means is that this is the radially outward distance dx, or you can say this is some distance dx. Now, where do you think the pressure would be more? To the right of this element or to the left of the element? So, naturally, to the right of the element, the pressure would be more. Now, you would be asking why? Why the pressure is more to the right of the element? It's because we have to rotate in a circular motion. So, in case of a circular motion, the inward force has to be there, which is provided by this extra pressure dP. The pressure acting in outward direction is P and in inward direction is P plus dP. We have to figure out what this dP is and we'll simply then do something with it, right? So, what is the mass of the element contained within this shaded part? Its mass is simply density into, let's say it has some cross section area, let's say S, into uh, cross section area is S into the length of the element dx. So whatever cross section area we have, that cross section area multiplied with the dx element, it will give us some volume, right? So that is what volume means. Cross section area into the volume into the length we are taking. So it becomes some volume. Volume into density gives us mass. So this is the mass of the element which we are considering. We will be basically providing centripetal force to this mass. So we'll say omega square x. Omega square x. This is the centripetal force required on this particle to keep it in circular motion. So there is the extra pressure into, right? This the extra pressure is providing that force. So what we'll do with the excess extra pressure dP, we'll multiply it with the surface on which it is acting, that is S, to give us this rho S dx into omega square x. This is S. This cancels out. And on integration, we get delta P is equal to rho omega square x square xf square minus xi square minus xi square by 2. So when we equate this change in pressure with this equation rho gy, if I increase, this is also the pressure difference, right? PB minus PC. So this PB minus PC will be equal to this delta P. When I equate this rho gy with this equation, I am getting a quadratic form, right? You can see here, this is y. So y is equal to some x square minus xi square. So this is a quadratic equation, right? That's why this is a parabolic curve or a paraboloid. Okay. So thank you for joining. Have a good day.